Welcome to the video on cutoffs, right? We'll do an example, right? And then we will be focusing on the how to cut reinforcement, right? Positive reinforcement at the support. And we start with our beam, right? This beam is the one that we are going to be working on a series of videos, right? Doing examples on how to cut the reinforcement. So this beam has normal density concrete F prime C equal to 30 MPa and steel reinforcement Fy equal to 400 MPa. Make the beam more efficient by removing steel where it is not required, right? So they are asking us to do the cutoffs for the reinforcement. So I have this load, right? I have this load and I have here, this is my dead load. And I have here illustrated the total load, I believe. Yeah, because this is the total load equal to 113.75. So if this is 113.75, then my dead load is 46.25. My live load, it is 67.5 kilonewton per meter, right? Dead load 46.25 kilonewton per meter, right? So these are the loads. Somebody else was kind enough to design this beam for us. So in the positive moment region, and you may be wondering, positive region, why, right? Well, because this beam would have this sort of moment diagram, right? So this is approximately it. Some positive moment and some negative moment. So in the positive region, right, we have this reinforcement, and then it is 5/30, right? 5/30, and then we have all the geometry that goes with it. In the negative moment region, we have 3/30, and we also have the geometry of it. So these 3/30 are these reinforcement, right? This reinforcement is 3/30, and this reinforcement over here is the 5/30. So they are asking where to cut this reinforcement. Here they are wondering if we can cut some of it, right? And then the rest, right? The rest. So this is what the problem is asking us. Well, in this problem, we are going to play with something called moment envelopes, right? We did a bit of it in the a previous lab, right? And it consists of placing the live load, right, which is the red load over here, in different spans. So the same live load, but in different spans, right, one at a time, while the live load is left on the two spans. And then with each loading case, we have a shear diagram and then one moment diagram. And then in the other loading scenario, we have a different shear diagram and another moment diagram. The point of placing this live load in different spans is to capture the most critical effects. So what we are going to do is to superimpose now the moment diagrams and the shear diagrams to get what we know as the so-called moment and shear envelopes. So I'm going to show you, right, the two different moment diagrams, and if we superimpose them, right, if we combine them, we can get that this is going to be our positive moment, and this is going to be our negative moment. So we can do the same thing for the shear envelope, right? And then right, but this is how it looks like for the moment envelope, right? Now, so the first step, right? The first step in this process is to right, and remember, right, we are talking about the positive reinforcement. So the first step is to identify which bars to cut, right? Which bars to cut. Well, for the negative, right? The negative top reinforcement, right? We will reduce the reinforcement in one stage. So we will cut the 3 theories, right, all at once. So, right, we're going to cut them all at once where we no longer require them, right? And remember, these will be the theoretical cutoff point, but we know that we have to extend it a little bit more, right, to find the actual cutoff point. That's for the negative top reinforcement. Now, for the positive, right, bottom reinforcement, it's just a proposal, guys. It's just a proposal. What if we cut, right, these two theories, right, at some given point, right, where we no longer need them, right, and then, right, we are going to cut everything later, right? So we cut the top two bars here, right, and at some point, right, where we no longer need the bottom three theories, we are going to cut them, right? We're going to cut them. So this is what we are going to be doing, right? So focusing on the positive reinforcement at the left support, right? So reinforcement and at the right, these are my top two theories, and this is my bottom three theories. So we're going to be looking at this area first, right? Positive reinforcement at the support. The first step is to calculate the development length, right, of the 30M bars at the bottom of that beam. So I have here our equation for development length, and I'm using 0.45. Remember, it's just the one in which we have a stirrup reinforcement bigger than AV minimum, right? That's why I'm allowed to use 0.45. Otherwise, I'll be using 0.6. Remember? Otherwise, 0.6 on that equation, right? On that equation, and then I'm going to just plug everything on that equation, right? Remember the K factors. This is for bottom bars, right, as opposed to top bars, right? It has to do with how compacted the bars are. This is for uncoated bars, regular rivet bars, right? This is for normal density concrete, and this is for 25 M bar or greater, right? We have 30s. So you can check in your table from the previous slides and see that these values will give you K factors equal to 1. When we plug numbers into this equation, we obtain that the development length for a 30M bar located at the bottom of this beam is 986 mils, right? So development length of these 30M bars is 986 millimeters. That's an important value because, right, we're going to be checking development and then do the curtailment, but development is something that we have to check. For example, right, we have to check if there is enough space to develop the bars at both sides, like both sides from the maximum positive moment. So here is my maximum positive moment. Here is what I need those bars to yield. And I have to check if I have enough space right and left to develop those bars. So just by looking at this, I see that there is enough beam, right, in the left-hand side and enough beam at the right-hand side to develop that yield stress at the where I have the maximum moment, right? So there is ample space to both sides of the maximum moment to develop the bottom bars, right, the 30Ms. So this check is fine, right? We do the development check and we do the curtailment. Remember, it's part of the same problem, right? It's part of the same problem. The next step, right, and then this is looking at the fact that you are going to have remember, if you have this beam as this, right, the moment diagram is going to be something like this, right, something like this, or probably it's more positive moment here, right, and then you are going to have to enclose, right, to be able to prove that you have a bigger moment resistance diagram than your factored than your factor moment, right? So it's important to know the moment resistance levels. So if I have the 530 M bars, the total moment resistance should be 923 kilonewtons per meter, right? If I cut the top two 30 M bars and I have only the bottom three 30 M bars, I would have 603 kilonewtons per meter. And you can see here that then the two bars are providing the difference, right? But that's not required at this point, right? At this point. So it's going to look something like this. This is my factored moment, right? This is my factored moment. And I have written here, right? This is my factored moment in red. My factored moment. And you see, according to the envelope, my total maximum factored moment is 956. The moment resistance with 5 bars is 923. And with 3 bars is 603. So right off the bat, I am lower, right? I'm going to be lower. So the difference here, right? Let me see. The difference here is 3%, right? So we are 3% lower. You know what? I wouldn't lose sleep on this, right? 3% is within the realm of acceptance. Remember that you are using phi c equal to 0.65, right? Here is my right, phi c here, right? These are the reduction factors for concrete, for steel, right? So I have some safety factors embedded into my moments, right? So 3% is something that doesn't make me happy, but they are not going to make me lose sleep. So assume acceptable for now, right? Ideally, we would like to have had maybe 960 kilonewtons per meter, right, or 1,000 kilonewtons per meter. At this point, 3%, we're going to assume it's acceptable, right? Nobody will go to jail because of 3%, right? So no worries. Ductility and flexural behavior is quite forgiving, right? No more than 3%, please. No more than 3%. So this is a diagram. We are going to aim to have, right, some diagram of resisting moment like this. And we're going to be below. Don't worry, right? Don't worry. So we're going to try to have something like this, right? Something like this. And then, right, so we're going to design the cutoff points and the development lengths so that we can have this moment resistance diagram, right? Diagram. So let's find the cutoff points for the positive reinforcement, right? So let's do this, right? Let's do this, and let's do it kind of graphically, right? Kind of graphically. So first step, right? Extend the point, right? Extend the line corresponding to the moment resistance of the 330s to find point 1, which is the intersection of the factor moment and the resistance of the three bars, right? So I am going to have this point, right, and this will be the theoretical cutoff point for the top, right, for the top 2 bars, right, since the bottom 3 bars, right, can take it from there, right? So you need the top 2 30s for this region, right? And then so you need 3 30s in the bottom, 3 30s, 3 30s, right? Plus the two 30s in the top, right? So you need everything here, right, in this region. But after that point, right, in this region, you can right. Let me just see. So for all this region, right, for all this region, shaded region, you need 530s, right? But for this region over here, right, for this region over here, you need only, right, you need only the bottom 3, right, 3, so the 330s. So this is the cutoff point, theoretical, right? cutoff point for the top 230 bars, right? That's not going to be the actual cutoff point, right? The actual cutoff point is going to be given by the shear and development requirements, but that is the theoretical cutoff point, right? So this is what this diagram shows here in the bottom, right? So the next step is to extend, right? We're going to extend those 230 bars. So that was the theoretical point. We're going to extend them a bit, right? By a distance dB cotangent of theta, right? By a distance dB cotangent of theta, which is, right? And then I'll show you later how to get dB, but it is 806 cotangent of 35, 1,150 millimeters, right? To find 0.2, right? To find 0.2. So in this case, dB was calculated for the case in which we have only the bottom 330 bars, right? This is conservative because dB is going to be larger, right? And then 0.2 will be a bit farther away, right? So D is 895, right? And dB is the maximum of 0.9 D and 0.72 times H. So we get our 806 mils, right? So dB cotangent of theta is equal to 1,150 150 mils, right? So I'm here, right, and you will see that I am keeping track of all my distances, right? I have some that we are not using at this point, but I'm keeping track of all my distances. For example, this is the intersection between the moment resistance of 3 bars and the factor moment, right? And then, right, this is 1,150 mils from here to here. I arrived to 458 mils, right? So I'm keeping track of the coordinate, right, or the coordinate of these points. So I have found point number 2, right? I have found point number 2, and then at this point I can direct my attention to the continuing bars, I believe. Yes. So what about the bars that go into the support, for example? It says at least 1/3 of the total reinforcement must continue into the support, right? If it's a simply support. So in this particular case, right, let's run all the 330s, right? All the 330s through the support. So 330s out of the 530s, like 3 over 5, I'm running 60%, right? The code says pass at least 33%. I'm running 60% of the total positive reinforcement, right? Through the support to the end of the beam, right? And this is why I, right, assuming a clear cover of 40 mils, right? I stopped here short, right? 40 mils. I stopped here to find 0.4. So I have 0.4, which is my 330s that I have run into my support, right? Now, the continuing bars, right? And here I have a useful number, right? So with some geometry, because this support is 300, right? This one over here is 300 mils, right? And if the clear cover is 40 mils, I can find this distance over here. I can find this distance, which is 110 millimeters. That will come handy later, right? It's the available length from the middle of the support to the end of the beam. So the next step is to see the continuing bars, right? These continuing bars, right? The continuing bars, these guys over here, right? These guys, the length, this length. The continuing bars must extend beyond the theoretical cutoff point. This is my theoretical cutoff point. Must extend the maximum of the development length plus D or development length plus 12 dB, which is 1846 mils and 1346 mils. Now, available space, right? So this is this distance. Available space is 1,708 millimeters, which is not okay, right? It's 8% lower, we're going to assume good for now, not good because it's acceptable, right? But we are going to continue because later we'll see that those continuing bars, right, the 330s here, will be specially anchored, so we don't have to worry about that requirement, right? But yeah, no, they don't pass, right? There is not enough length to continue for those continuing bars, right? But you will see in a minute that we'll anchor them especially, and those bars will be fine, right? Okay, so that takes care of the bottom 3 bars, and then let's think about this location, right, where the moment is 0, right, where the moment is 0, and we know that at the simple support, right, and this may ring a bell. Remember, we have to check something at the middle of the support, right? Remember the anchorage force. Remember? Okay, so the first question is, right, so I have my bottom 3 bars in the middle of the support, right, where the moment is 0. And then you may remember, oh, Carlos, didn't you say, well, instruction, didn't you say that we have to extend the reinforcement past the point in which we need that we need it for flexure? We need to extend the dB cotangent of theta the same way that we extended the 230s here. Shall we extend the 330s by a distance dB cotangent of theta as well, right? Shall we do that? But we said, right, that before that we don't require the extension of these bars at the supports or the inflection points, but we must check, right? We kind of exchange that requirement for this one. We check the additional shear capacity using one of these 2 equations, right, as applicable. BF minus 0.5 VS cotangent of theta, or 0.5 BF plus VC cotangent of theta. This one, if AV mean controls. So this means that I have low shear, and AV minimum was enough, right, to have good shear design, right? So we don't know at this point what case do we have, right? But if we remember, right, this beam is something like this, right? So the moment diagram is something like this, and the shear diagram is something like this, right? So in this location, right, in the middle of the support, right, the shear is high, right? So it's it's reasonable to think that we are in the first case, right? So we are in this case in which we have to quantify or we have to use that anchorage force, because we are so near from the support, and there is a large shear there, right? We haven't heard about the stirrups. What's the spacing of the stirrups for shear at that point? I think we are going to have to assume something there, right? So if we assume that near the support there is high shear, if we assume 10 mm stirrups at 300 mils, and then, right, I can almost hear you ask, well, do we have to assume? No. You are working on an already designed beam, so you will know the spacing of the stirrups at this point and what type, right? So this means that AV is bigger than AV minimum, right? So we'll be checking the first equation, right? The first equation. So that first equation was BF minus 0.5 VS, right? All multiplied times the cotangent of theta, right? So factor shear is something that we can get, right? That we can get easily from the shear envelope, just looking at those shear diagrams that we had on the previous slides. And VS is something that I can calculate, because I know that the stirrups are spaced at 300 mils, and cotangent of theta, I know that it's 1.43, right? So it's something that I can calculate easily, right? That anchorage force. And again, we are looking at the forces here, right? This is a check that it's being made here, right? This is the tension force due to shear, right? We have to check if our reinforcement is able to take this this force, right? This force. Okay, so well, let's do it, right? From the shear envelope, the factor shear is 466 kilonewtons, right? So Vs is given by this equation, right? AB dV cotangent of theta, phi Fy divided by S. So 200, this is the two legs of 10m stirrup. dV is 806, we got it from before, cotangent of theta 1.43, phi S 0.85, Fy 400 megapascals divided by spacing of stirrups, assumed in this case as 300, we get 261 kilonewtons. T due to shear, tension force due to shear, Vf minus Vs cotangent of theta, 466.4 minus 260 times 1.43 gives me 294 kilonewtons, right? So, okay, I had 330s there. The total capacity of those guys is, total capacity is area of steel Fy equal to 2100 times 400, 840 kilonewtons to develop, right? So this is the total force that 330s can develop, but we are developing 294, right? 294. So at first glance, we would consider it correct, right? Because it's much less. But this has to do with development length, right? Now, to develop the full yield force, 840 kilonewtons, we just found that these 30M bars need 986 millimeters. Do you remember? That was the development length. So how much embedment they need to develop 294? So it's a proportion, right? To develop full force, they need 986. To develop 294, how much embedment they need? So it's just a simple proportion, and they need 345 mils. Do we have 345 mils, right, within the support? And if you remember, we already did that, right? This is this distance over here. So it is half of the support width minus the cover, and that is equal to 110 millimeters, right? So not enough. We needed 345 mils, and we only have 110 millimeters, right? That embedment length has to be less than the maximum of these two values, right? So I have 895, right? So, but the one that I have, of course, is 110, which meets that requirement, but is less than 895. So when I compare 110 millimeters against what I need, I don't have enough, right? And then you may say, oh, wait a minute, right? With a straight bar, you cannot develop it there. But what about a hook, right? What about a hook? We investigate if we can use a hook, right? So the basic hook design length is given by this equation. 545 mils is what we get when we enter the diameter of the bar in F prime C, and we obtain a basic hooked length, which is now lower, right, at the 986 we have. And then we remember, right, full capacity 840 kilonewtons of the 330s will require 545, and 294, which is the tension caused by shear, will require 191, right? 191 is still bigger than the available space that we have to place our hook, right? which is 110. So in this particular case, we are going to use we could add bars, right? We could add a few bars to carry these 300 kilonewtons. So for example, if let's say a 15M bar, right? A 15M bar with a cross-section area of 200 square mils, right, would be able to carry, let me just do it for you. So 200, so at yielding, right, they will be able to carry 80 kilonewtons. So we have 294, so we will need about 415Ms, right? So 415Ms will take care of the force. If you use let's say 20s, right? 20 amps. These guys are 300 square mils, right? Times 400 megapascals. So these guys 120 kilonewtons. So we are carrying 294 divided by 120. Yeah, about 3, right? 320s. We can add these segments, right? And then we would be able to carry 294 kilonewtons, right? 294 kilonewtons. So in this particular example, I'm going to show you that you can use special hardware, right? For example, if you use a T-headed bar, right? A T-headed bar, right? If the hook doesn't work, a T-headed bar is just a bar that is welded or attached to a plate, right? And then the idea is that all the force is going to transfer via bearing, right, to the concrete, not through bond, but through bearing. And remember, bearing will take. I mean, it's going to be very effective, because it's going to transfer just those forces into the concrete in compression, right? All this concrete here is going to be in compression, right? When you pull from that bar, right? And then with a relatively small area, you will be able to take all the force in that bar, right? So when you use these proprietary systems, right, you buy the hardware, you read the instructions, and then some of these T-headed bars that you need to make a pocket on your concrete, right? Sometimes you just attach it on the surface, right? Depending on your application and depending on the your particular constraints, right? It could be inside of a pocket or just right in the outside of your beam, right? So these T-headed bars, right, allow for full development of the bar with negligible development length, right? So they can develop the yield right where the plate starts, right? They can give you Fy instantaneously, right? Instantaneously. So we finished with the anchorage, right? We assume that using the special hardware, the bottom 330 bars can develop their yield strength right at the beginning. So we can develop the a full moment of 603 kilotons meter right at that location, right? Remember that if we have normal bars, right, it will take us a little bit, right? It will take us a little bit to develop the bar, right? If we had the space to place our bar, we would have to check now the slopes, right? The slope of the bar, making sure that the slope of the resisting moment is bigger than the slope of the factored moment. And since we have a strong support in compression, we will be able to use this equation, right, where we check the slopes with the 1.3 parameter, right, with the 1.3 parameter. If it was a normal bar and we had enough space, right, this will be the slope we will get, right, starting from 0 to some value, right, 603 kilonewtons meter, right, and then 1.3 in the equation because we have a compressive action from the support, and these will be the values that we would use on our system, right, on our system. So the 1.3, right, the resisting moment for the 330s, which is 603, right, and then the factored shear 464 kilonewtons, and this is the available embedment length, right? All of it should be greater than LD. So this is the equation that we would be using if we had been able to use a normal bar. But in this case, right, we don't need to check the development using that equation, right, because our bars develop the full moment right at the beginning, right where the anchor is. So we start at 603 right here because of our headed bar, right? Because of our headed bar. Good. So okay. So we find, right, at this point we find the 230s, right, at the top, and we need LD to develop them, right? So LD for 30 bars is 986. So the bars will need 986, right? The two 30s, right? The two 30s will need 986 millimeters to develop, right? So I have placed that length here, right? So 1444 millimeters. So they will develop here, right? Once they reach, right, here is when we reach 923.1 kilometers per meter, and then from there is no change. They will stay constant, right? Stay constant, and then right 3% difference, right? I won't lose sight, right? But you should try to make your designs a bit better than mine, right? So yeah, no, it's 3% is acceptable enough to have this development. So what we have is, yeah, well, most of our resisting moment diagram is exceeds the factor moment. So our cutoff points are quite all right, right? Quite all right. So we finished telling the positive reinforcement, right, at the support, and then we have interesting things ahead of us, right? We have to detail the positive reinforcement at the inflection point, and then later we'll detail the negative reinforcement, right? The negative reinforcement. Well, perfect. Thank you very much, and see you on the next video.